This is the first PowerPoint in Chapter 14, and Chapter 14 is the beginning of a series about chemical equilibrium. Most chemical reactions are reversible. Not all of them. Like I'd like to see you try to reverse a combustion reaction, right? But most of them actually are reversible. And when I mean reversible, I mean, and this is kind of off kilter here a bit, products in the beginning are there aren't any in the beginning typically, right? But as products build up, the reaction can go in the reverse if it's a reversible reaction. In other words, the products can react with each other to regenerate the original reactants. So chemists show that either with a set of two arrows showing that the reaction is reversible, or you can write the reverse reaction separately. Equilibrium. Okay, this is really important. It seems like a simple definition, and it is, but it's really, really common for students to forget what's equal in equilibrium. Equilibrium means the rates are equal. So that means the rate of the forward reaction equals the rate of the reverse reaction. Equilibrium has no information about the relative amount of reactants and products that are present. And that's a huge mistake that students make. They think equilibrium says something about the relative amounts of reactants and products. It absolutely does not. It is only the relative rates of the forward and reverse reaction. Make sure you have that down, okay? There are a couple of graphs that are commonly used when talking about a reversible reaction. And so let's look at them one at a time. One is if you plot concentration versus time. We saw a lot of this type in our kinetics chapter, because remember that the change in concentration over change in time is the rate of a reaction, right? And and we learned that the rate of a reaction typically slows down. In other words, the slope of this curve gets more and more shallow as time goes on. And so we can see for reactants, such as A, if we have a reaction now, we're just talking about A going to B, that the amount of A is going to decrease over time, and the amount of any product, B, why is that not writing, is going to increase over time. At some point in a reversible reaction, the change in concentration of reactants and products are going to stop changing. So do you see now where the concentration of the reactant A levels off and the concentration of B, the product, levels off? This leveling off point means equilibrium has been achieved. So I guess I take back what I said a minute ago. Equilibrium gives you some information about concentrations, but the only information it gives you is that the concentrations of reactants and products stop changing, okay? It doesn't tell you how much there is of either one, whether you have more reactant or more product. It does not tell you that, all right? So anyway, so that's one graph, and the other type of graph is simply looking, instead of the change in concentration over time, the rate with time, okay? And so remember what the definition of equilibrium is. It's when the rate of the forward reaction equals the rate of the reverse reaction. So the blue represents the rate of the reverse reaction, and the red represents the rate of the forward reaction. And when those two rates are equal, that is equilibrium, okay? All right, so be able to interpret those two type of graphs. All right, so just to kind of reiterate what I said, at equilibrium, there is no observable change in concentration of any of the reactants or products. So you can determine equilibrium by monitoring concentration and looking for it to stop changing, or you can also monitor rate, but that's a little more complicated because you have to monitor the rate of the forward and the reverse reaction to see when they're equal. Now, chemical equilibrium, you will often see it called dynamic equilibrium, simply because it appears when you're monitoring, let's say, change in concentration over time, it appears that the reaction has stopped because you're like, okay, concentration of reactants, concentration of products are not changing anymore. The reaction stopped. No, it has not stopped. Okay, it has stopped changing, but reaction continues to go forward and backward at the same rate. That's where the dynamic descriptor comes in. All right, so just kind of convention to make sure you're up on the convention. The type of arrow we're used to seeing in a chemical reaction is just a single-headed arrow, which means yields, right? You're going to start seeing more of now that we're talking about reversible reactions and equilibrium is two arrows, opposite directions. And just a note, do not confuse these two separate arrows pointing in opposite directions with the double-headed single arrow that we use to designate resonance structures. And this is not going to be dynamic in here apparently, but this little GIF that I stole, it makes the point that these little ants are moving or marching at the same rate back and forth, and they're carrying whatever these little grains of rice or whatever they are that they like. And this is making the point that the rates of the forward reaction are equal at equilibrium, but the amount of reactant and product are not equal. They may occasionally be equal, but that would be a total coincidence. Alrighty, let's move on to how do we mathematically represent equilibrium. So we have something called equilibrium constant, which is a capital K. Why do we always make things so similar? Because remember, the lowercase k is the rate constant. Now I want to take a minute and show you where equilibrium constant comes from. It's very logical origin. Now you don't have to, at least in my class, you don't have to show the derivation, but it's good to know. So let's assume we have a really simple reaction and that it's reversible and that happens to be at equilibrium. So since it's at equilibrium, we know that the rate of the forward reaction equals the rate of the reverse reaction. Now, if you can remember all the way back to kinetics and rates of reaction, the rate of the forward reaction, assuming this is a one-step reaction and it doesn't have a complicated mechanism, but the rate of the forward reaction could be expressed like this, right? Rate constant times concentration of reactant, and assuming again that it's a one-step reaction so we can treat it like an elementary step, the coefficient of 2 becomes the exponent. Now, the reverse reaction, which would be, right, the product N2O4 going to 2NO2, the rate expression for that reverse reaction is some rate constant times concentration of the reactant, which in this case, in the reverse reaction, it's N2O4. All right, so now we have the rate for both the forward and reverse reaction, and if we're at equilibrium, the rate of the forward equals the rate of the reverse reaction. Now, let's rearrange this so that we put the constants, the rate constants, on one side and the concentrations on the other. What do we have here? So we're going to call the ratio of the rate constants big K, equilibrium constant. And what is it equal to? It is equal to the concentration of the product, at least the way we have it arranged here, over the concentration of the reactant. Now notice that the exponent, the 2, in an equilibrium constant is from the coefficient in the balanced reaction. Remember, we can only do that in rate expressions when it's an elementary step or one-step reaction. But in equilibrium constants, automatically the coefficients become exponents, right? So that's a big difference between rate constant and equilibrium constant. I'm going to pull that up. Make sure you know what I'm talking about here. All right? So always, when writing equilibrium constant expression, whatever the coefficients are automatically become exponents. So notice it's products on the top, right, over reactants on the bottom. All right, so the generic formula for an equilibrium constant expression is this. So it's concentration of each of the products, okay, multiplied by each other, and raised, this should be a little d here, and raised to the exponent that equals their coefficient, divided by concentration of each of the reactants. Again, the coefficients in the balanced reaction become exponents. You will occasionally see equilibrium constant in terms of pressure instead of concentrations. That can only occur when you have at least one gas in the reaction. Now, all of the substances in a reaction don't have to be gases in order to use Kp. Okay? At least one of them does. And this is me, just like I do, repeating things multiple times in hopes that it'll sink in, that it's important. So this is just my reminder again that in an equilibrium expression, the coefficients become the exponents, okay? Whereas we can't do that in kinetics unless it's in an elementary step in a mechanism. Alrighty, let's actually work some examples. Let's look at this reaction. And what if I told you to write the equilibrium expression? Okay, so remember it's products, concentration of products. Coefficients become exponents. And divided by concentration of reactants. Alrighty, so pretty simple, right? There are a couple of exceptions that you need to keep in mind. The most important exceptions are that solids and liquids are not included in equilibrium constant expressions. Okay, notice that these gas, aqueous is also allowed. Now, it's very logical why this is the case. Okay, pure solids and pure liquids do not change their concentration, right? They're not getting dissolved in something and diluted. So they have a set concentration, like water's, I think 55.5 molar, right? That concentration is not changing. It's a constant. And so they're not totally left out. They're just lumped into the equilibrium constant, okay? Their values are not going to change, so they're not over on the variable side. All right, let's do a couple more equilibrium expressions, keeping in mind that solids and liquids are not included. All righty, this one's pretty straightforward. Okay, reactant and product are all gases. Now remember, we could write this, since we have gases involved here, we could write that as the pressure, partial pressure of O2 cubed divided by the partial pressure of O3 squared. Okay, you get a slightly different value usually than the regular concentration equilibrium expression, but you could if you were asked. Okay, let's look at the bottom one. Again, we don't have any solids or liquids, so it's pretty straightforward. But let's look at the very last one now. This is really weird. I remember the first time I saw one like this, I thought, this has got to be wrong. But the equilibrium constant expression for this reaction is simply dependent on concentration of CO2. That's the only substance that isn't a solid or liquid. Okay, so that's it. That's the only variation you're going to have when you're calculating equilibrium constant is CO2. The others are going to be constant and never going to change. Let's talk about the numerical value of the equilibrium constant. Now, just to kind of remind you of the formula for equilibrium constant, it's concentration of products over concentration of reactants. So what's going to make an equilibrium constant larger? When you have more products, right? Now, these are the concentrations at equilibrium, okay? Not just any old place in the reaction, at equilibrium. What's going to make the equilibrium constant smaller for a reaction? If you have a large amount of reactants, okay? So keep that in mind. So any K value that is larger than 1 means that products are favored. Means that you have more products than reactants. Any equilibrium constant that is less than 1, that is some fraction, means that reactants are favored, or there are more reactants at equilibrium. K is unitless. It wouldn't have to be, obviously, right, because its concentration is raised to some power, but we would have crazy units like molarity cubed or 1 over molarity to the 5th. They're just nuts units, and so they just decided it's unitless. And just kind of a picture to drive home what a numerical value of K means. So if K is large, and by large, I mean you'll see on the order of 10 to the 6th, 7th, 8th, 10th, 20th, really, really large numbers sometimes. That means that products are favored. If K is small, particularly less than 1, that means that not very many products are present at equilibrium. So bottom line, what does a very large or very small K value tell us about the reaction? It tells us about the extent of reaction. How far to completion can we expect reactants to take us at equilibrium? That's really important for industrial chemists, right? Because if they're looking to make a certain product, they want to make a lot of that product. They want it to be an efficient reaction. They don't want it to proceed 10% and stop, right? So in industry, you want a very large K value. So here's a ridiculously large one. Yeah. All right. So if you, similarly, if you have a very small K, that means you don't have very many products at all. Okay. So remember, scientific notation, if you have a negative exponent, what does that mean? That means the number is very small. Okay. And that means not very much product. Not much product, all right? Now, there are some intermediate values, and in general, between K values of between 1 and 10 are considered roughly equal amounts of reactant and product, okay? It's not really fair to say that it's reactant favored or product favored if you have a moderate K value. I want to spend a few slides and tell you about how K can be manipulated or compared from one reaction to another. So let's look at this generic reaction. A plus B goes to C. If we reverse the reaction, how does the value for the equilibrium constant change? Well, let's go ahead and I'm going to write it out in detail so you can see it yourself. So here's the expression for the forward reaction, right? Products over reactants raised to their coefficients. And if we write the equilibrium expression for the reverse reaction, what is the relationship between these two equilibrium constants? Okay, it turns out that the equilibrium constant in one direction is simply 1 over the equilibrium constant in the other direction. In other words, you can flip either one of these. So put the denominator in the numerator in the denominator, and you get the other one. So here's one kind of little formula you need to remember, okay? It's K, equilibrium constant in one direction is 1 over the equilibrium constant in the opposite direction. The other common manipulation that you need to understand for equilibrium constants is if you have a reaction, again, here's our generic reaction, if you multiply it by some coefficient, okay, in this case we multiplied everything by 2, right? So if you multiply it, that multiplying factor becomes an exponent. So multiplying a reaction by 2, that 2 becomes an exponent. And so you can see, hopefully you remember your math, that when you have an exponent to an exponent, you add them, right? So the resultant equilibrium constant is simply the original equilibrium constant squared. So those are the two most common manipulations that you need to be comfortable with. And here's a specific example problem with actual numbers. So here's a reaction, our base reaction. Now, what if you were asked to determine equilibrium constant for the following reaction? The first thing you have to do is decide how has it changed. Okay, what have we done here? Well, we have reversed it, right? Have we done anything else? No, because coefficients are the same, right? So then you need to remember, what is the new equilibrium constant for this reaction going to be? It's going to be 1 over the original one. Of course, you'd have to plug that into your calculator. Don't leave it like that. All right, let's do another one. Let's look at this reaction and figure out what the equilibrium constant would be. Well, what has changed? Go back to the original reaction, and what has changed there? We have reversed it again, right? But we've also changed the coefficients. So find the multiplicative factor, I think I made up that word, that you multiplied the reaction by to get this one on bottom, okay? I'm just going to say we multiplied the whole thing by 1/2. The same thing as dividing by 2, right? But if you multiply, it's easier to manipulate the k values. Okay, so we multiplied, so we reversed it, and we multiplied it by 1/2. So reversing it is going to do 1 over the k value like we did in the previous sample problem. Okay, and then multiplying by 1/2 is like raising that to the 1/2 exponent. And again, hopefully you remember your math that if you raise something to 1/2 exponent, that is the square root, right? All right, so our new equilibrium constant would be 1 over the square root of the original equilibrium constant. So here are them, the results presented a little bit more neatly for this reaction, right? When we plug 1 divided into 4.63 times 10 to the minus 3, here is our new equilibrium constant. Notice a couple things that kind of make sense, right? The original equilibrium constant is small, right? You have a negative exponent, which means the reactants are favored, which means at equilibrium, you're not going to have very much of that. You're going to have mostly the reactant left. The reverse reaction, you would expect the opposite, right? So the reverse reaction that's a relatively large K value, which means the products are favored, which is what you would expect, right? So in both cases, the dinitrogen tetroxide is favored. So it's not going to change the substance that's favored, depending on which way you start. All right, so calculate an actual number for the second sample problem. Well, this is interesting because on the last page, I had it reversed. So on the last page, if you noticed, I had it written as, in other words, I had reversed it and multiplied. In this page, I'm changing it. I don't want to confuse you. All right, so let's just go with what we saw on the last slide. The reaction is multiplied by 1/2 and it's reversed. So it's going to be 1 over the square root of 4.63 times 10 to the minus 3. And so I'm going to go ahead and calculate that now. Let's see. And the answer I get then is 14.70. This is even wrong. I need a proofreader. There we go. That should have been that. Okay. So anyway, if you reverse the reaction and multiply it by 1/2, you get 14.70. So just kind of check, make sure you're comfortable with doing that math. I mentioned at the beginning of the PowerPoint that sometimes the equilibrium constant expressions are shown in terms of pressure, and you can only do that if you have at least one gas present. So instead of using concentration units, molarity, we use pressure, partial pressure of each component. But other than that, it's done the same. Now, equilibrium constant in terms of pressure is usually a different value than equilibrium constant in terms of concentration. And so this formula, if let's say that you're given pressures of components, so you're going to calculate Kp, but then let's say the problem actually asked you for Kc in terms of concentration, you would use this formula. So let me go over what's involved in this formula. So R is the universal gas constant, which I've said before shows up everywhere in our world, right? And the value we're going to use for that is the liters, atmosphere, mole, Kelvin. And temperature, of course, to match the R value has to be in Kelvin. And what's new and of note here is the delta N. What that means is the difference in the number of moles on the product side versus the reactant side, number of moles of gas. Difference in the number of moles of gas of products minus moles of gas of reactants. So we're going to do an example. So, but I want to point out at this point, there are some cases where Kp equals Kc. When will that happen? When will these two actually be equal to each other? When this whole portion equals 1, right? What's going to make that whole portion equal 1? When any exponent of 0, right? So if the difference in the number of gas on the reactant and product side is 0, if they have the same number of gas particles on both sides of the reaction, then Kp will equal Kc. Here's a sample. Most of the time you'll actually have to calculate one of them first, but I just gave it to you for this one. If the K value equals this, for this reaction, calculate Kp. So obviously the first thing you want to do is write down the formula. Oops, okay, messy. Okay, so we were given Kc. The R value you used is the 0.0821 liters, atmosphere, mole, Kelvin. Make sure temperature is in Kelvin. I was nice and gave it to you in Kelvin, but that probably won't usually be the case. Now, the exponent is what I want to focus on. It is the number of gas molecules on the product side. So you literally go to the product side, look at the coefficients, add them together for the gases. So there are 2 gas molecules on the product side. How many gas molecules are there on the reactant side? We assume there's a 1 here, right? So 2 plus 1, there are 3 gas molecules on the reactant side. So the exponent is -1, so it has to be products minus reactants. When you do all that math, and I think you should pull out your calculator and make sure you're punching everything in right, or let me know if I did or did not. So the Kp value you get here is going to be different, and here it is. Not hard. And that, my friends, is it. Now, this is just the introduction to equilibrium PowerPoint, and how to write equilibrium expression and how to manipulate it.